Hello everyone, welcome to video lecture of ME312 Metrology and Instrumentation. I am Manu Joseph, Assistant Professor, Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. Module 5, Lecture number 3. In lecture number 2, we have discussed about performance characteristics of measuring instruments, where we discussed about two performance characteristics. One is static characteristics and other one is dynamic characteristics. Now we are moving to a new topic which is called transducers. A transducer is a device which converts energy from one form to another. So it can be also be defined as it's a device which converts a physical quantity into proportional electrical signal. So final output will be electrical signal. Okay. In lecture number 1, we found that in a generalized instrument, generalized measuring system, we have a primary sensing element first. So it gives out a signal. It should be converted to a easily manipulated form by a primary conversion element. Okay. So here in transducers, we are doing that conversion. In electrical transducers, we are doing that conversion along with the sensing the signal. Okay. So a transducer uses many effects to produce such conversion. It can be resistant effect, or it can be a inductance, it can be a capacitance variation that result in this conversion of a physical quantity to a electrical signal. The process of transforming signal from one form to another is called transduction. Here in the block diagram we can see a non-electrical quantity. This is a non-electrical quantity. So this is a primary physical quantity, and it is sensed by a sensing element, and the output of the sensor or response of the sensor is sent to a transduction element. So this transduction element converts this output of the sensor to an electrical signal. So this is the process of transduction, or this is the process what happens in a transducer. So a transducer will have basically two main components. One is a sensing element and another one is a transduction element. The physical quantity or rate of change is sensed by this part of the transducer. Now the transduction element, the output of the sensing element is passed on to transduction element. This element is responsible for converting the non-electrical signal into its proportional electrical signal. There may be cases, there are certain cases, this transduction element perform both transduction and sensing. Both the process are performed by the transduction element. Example, a thermocouple, where we have two junction, a hot junction and cold junction. One of the junction is kept at reference temperature, and other one is kept in contact with the bodies whose temperature is to be measured. And we have a voltmeter that's used to measure the voltage generated. Okay. So final output of the transducer or final output of this thermocouple is a voltage variation, such electrical quantity. Therefore both transduction, the sensing and the transduction is happening in same instrument. Therefore it is a transducer which comes under this category. Now we are moving to the classification of transducers. The transducers may be classified according to their application. First is application, the method of conversion, method of energy conversion, the nature of output signal, so on. This diagram represents the basic classification of a transducer. So transducer, on the basis of its transduction process, is resistant, resistive, capacitive or inductive. And then we have primary and secondary transducers, active and passive transducer, analog and digital transducer, then transducers and inverse transducers. This is the basic classification of a transducer that we will study in detail. So first we will discuss about active transducers and passive transducer. The first is active transducers. So active transducers, they are transducers which do not require any auxiliary power source to produce their output, or they can be considered as self-generating devices operating under energy conversion principle. They are self-generating. They do not require any external power source. They generate an equivalent electrical output signal based on the input. Example, the energy or pressure to charge or temperature to electric potential. The pressure to charge is happening in a piezoelectric crystal. It's an active transducer. Temperature to electric potential is happening in a thermocouple. That is also an active transducer. The energy required for the production of output signal is obtained from the physical quantity being measured. So the applied pressure will be the physical quantity for a piezoelectric crystal. So it generates energy for the output from this input. So measurement of velocity, temperature, light intensity, force can be transduced with the help of active transducers. Example, piezoelectric crystal, thermocouple, photovoltaic cell. Now this represents a piezoelectric transducer. When external force is applied, this is an external force. When external force is applied, there will be a change in the voltage generated across the surface. That will be detected by a voltmeter. So there is no external supply for it working. So this is an active transducer. Now passive transducer. So these are devices which require external power or derive the power required for transduction from an auxiliary power source. They are also known as externally powered transducers. Other one is self-powered, self-operated transducer. This is also called as externally powered transducer. They also derive part of the power required for conversion from the physical quantity under measurement. Example, resistance thermometer and thermistors, potentiometric devices, differential transformer, photo emission cells, strain gauges, etc. They require an additional power source. So in strain gauge, we have a Wheatstone bridge arrangement, and the terminal of the Wheatstone bridge is connected with a external power source. Okay, and based on the strain, the resistance or the one of the arm of the Wheatstone bridge will changes, and as a result there is a net voltage in the output side of the Wheatstone bridge. Here you require an external power source for its operation. Therefore it is a passive transducer. Next classification we are going to discuss is analog transducer and digital transducers. So analog transducers and digital transducers. So analog transducers, these transducers convert the input quantity into analog output, which is continuous function of time. This output is analog. Another one is digital transducer, which convert input quantity into electrical output, which is in the form of pulse. This pulse output is not continuous one. The output is the pulsed output. It's not a continuous one. That is digital transducer. Then we have a primary transducer and a secondary transducer. The transducer which converts the physical quantity into mechanical displacement is a primary transducer. Here in the primary transducer, the output is not an electrical signal. is some other physical signal, that is here into a mechanical displacement. Example, Bourdon tube, diaphragm, bellows. Bourdon tube, we know when we apply pressure using, or when we want to measure the pressure of a particular fluid, when we use it Bourdon tube, the tube will have a displacement. The output is a mechanical displacement. Such transducers are primary transducer. So another one is secondary transducer, transducer which convert mechanical displacement into electrical output. That is a secondary transducer. So output of the primary transducer is converted into useful signal by secondary transducer. That is, output of a primary transducer is a displacement. It should be transferred, it should be converted to a electrical signal. It should be done by secondary transducer. Here is this example, LVDT. Here in this example we can see the pressure measurement. We have a Bourdon tube which is connected to a LVDT, that is linear variable differential transformer or linear variable differential transducer. And when the pressure is applied, or when it used for pressure measurement, the pressure of the fluid in the medium will cause this Bourdon tube to displace. It will displace the Bourdon tube. As a result, that displacement motion is carried by this connection to the core of the LVDT. This is called core of the LVDT, field core of the LVDT. So this LVDT will move up or down. So when it move up or down, the induced EMF in the secondary coil will vary based on its movement. That will give a output voltage. So here the output of this LVDT is an electrical signal. That's electrical output. So this will be a secondary transducer. This is the secondary, the LVDT is the secondary transducer, and Bourdon tube is the primary transducer. So next classification is based on the principle of transduction. Based on the principle of transduction, we have resistance transducers, inductive transducers, capacitive transducers, thermocouples, piezoelectric transducers, optical transducers, and photoelectric transducers. So in capacitive transduction, in the measured capacitive transducer, the measurand is converted into change in the capacitance. The measurand is converted to change in the capacitance. So in the capacitance we know two plates. In capacitor we know there are two plates and it's filled with a dielectric medium. Its gap is filled with a dielectric medium. So by changing the distance between the plate or changing the dielectric medium, there will be a variation in the capacitance. That principle is applied for transduction. So change in capacitance occur either by changing the distance between two plates or by changing the dielectric. So that is what is happening in capacitive transduction. Then we have electromagnetic transduction. In electromagnetic transduction, the measurement is converted to voltage induced in the conductor. So this displacement of this magnet resulting that induces a voltage in this coil that will be detected by a voltmeter. So here the voltage induced in the conductor by changing the magnetic flux in the absence of excitation. There is no excitation here. So the electromagnetic transducers are self-generating active transducers, because it's self-generating means it do not require external power source, and it can also be a secondary transducer because its output is electrical. So the motion between the piece of magnet and electromagnet is responsible for the change in flux here. We are applying Faraday's laws of induction, that is electromagnetic transducers. That here we have a magnet. The movement of the magnet will vary the flux linked with this coil, and as a result a EMF is generated, and that voltage is measured, potential difference is measured with the help of a voltmeter. Then is inductance transduction. In inductance transduction, the measurement or measurand is converted into change in the self-inductance of the coil. Okay, so that is in induction transduction, the physical quantity causes a change in the inductance of the coil. It is achieved by displacing the core of the coil that is attached to the mechanical sensing element. Example is LVDT, that the principle and working of the LVDT will be discussed in the coming slides. Now, piezoelectric transduction. In piezoelectric induction, the measurand is converted into change in electrostatic charge Q or voltage V, and generated by the crystal when it is mechanically stressed. So we have seen that. So here a crystal, when force is applied, so there is a change in the charge accumulation, and that will give out a voltage. So that is what is happening in a piezoelectric transduction. So that's about different transduction, and apart from that, I already discussed the some of the transducers classification based on the principle of operation, that's capacitance, piezoelectric, electromagnetic, etc. Other than that, we have resistance transducers, where the resistance of the transduction element varies with the physical quantity. Resistance varies. Example, strain gauges. The strain gauge is a passive transducer, where the strain gauge consists of a resistive element. When we apply stress, some elongation will happen in the resistive element of the strain gauge. As a result, resistance varies, and that will be measured as a change in the electrical signal. So that is a transducer which works based on the principle resistance variation. And then we have a thermocouple. We already discussed, and also we will study in detail in the coming module. Now, transducer and inverse transducer. The transducer we already discussed, it converts non-electric quantity into electrical quantity. Non-electrical quantity into electrical quantity is the function of a transducer. In inverse transducer, it's the inverse of a transducer. Here, inverse transducer convert electrical quantity into non-electrical quantity. An electrical quantity is converted to non-electrical quantity, that is inverse transducer. So piezoelectric crystal can act as an inverse transducer, because when a voltage is applied across its surface, it changes its dimension, cause mechanical displacement. So a non-electrical or mechanical displacement like mechanical vibration. That is, when we take a quartz crystal and when we apply electrical signal, so that will vibrate. So that is converted to the electrical quantity to non-electrical quantity conversion is happening. So that is inverse transducer. That is about the different classification of transducers. We found that we have different classifications. That is base of transduction: resistive, inductive, capacitive. Then we have primary and secondary transducer, analog and digital transducer, active and passive transducer, transducer and inverse transducer. Now we are moving to motion and displacement measurement. First we will have an introduction about the importance of measurement of motion and displacement. Then we will discuss about method of measuring the displacement or motion. So in introduction, the displacement and speed are two important parameters whose measurement are important in many position and speed control applications. In position and speed control application, we require the measurement of correct measurement of displacement and speed. So error-free measurement of these two parameters are necessary in order to achieve good control of performance. So good control of performance of many activities. For example, a machining operation. The correct measurement of correct machining to happen in a CNC, correct feedback system should be needed. So displacement, the position of the tool should be properly identified. So then that can only happen if the displacement is properly measured. So displacement measurement can be of different type. There are different types of displacement measurements with the help of LVDT, with the help of potentiometer, etc. And displacement may be in the range of few microns, that is micrometer range to centimeter range. Moreover, the measurement may be of contact type or non-contact type. Can be made contact type or non-contact type. That is, this displacement measurement we have different types of displacement measurement based on the range of measurement, based on contact or non-contact type, linear or angular measurement. Okay, so similar speed measurement also we have different classification. In the displacement measurement can be of two type again, contact and non-contact type. Based on the measurement principle, it can be classified into two categories: electrical sensing and optical sensing. Once again classified as electrical sensing and optical sensing. So in the electrical sensing, the passive electrical sensors are used and the variation of either inductance or capacitance with the displacement is measured. That is electrical displacement measurement, electrical sensing, passive electrical sensors, okay, where variation either inductance or capacitance with the displacement is measured. Optical method, that here the LVDT is an example. We have seen in body and tube, the displacement is transferred to a transducer where there's a change in the inductance, so it's a passive transducer. And finally, the electrical signal, give electrical signals. Optical method mainly work on the principle of intensity variation with the light and intensity variation of light with the distance. So change in the intensity of light with the distance. That's the principle. So interferometric techniques, optical method, the interferometric technique is also used for measurement of very small displacement in the order of nanometers. And but we have already discussed about the interferometers. But this technique is more suitable for laboratory. The interferometric technique is more suitable for laboratory purpose, not very useful for industrial applications. Now we'll start with potentiometers. The potentiometers are simple type of displacement sensors. It's a simplest type of displacement sensors. So here they can be used for linear as well as angular displacement measurement. they are resistive type of transducers and output voltage is proportional to the displacement. So potentiometers can be defined as is a resistive type of transducer. Resistive type of transducers. That means the output of the transducer is based on the resistance variation. The output is voltage, which is proportional to the displacement. The major problem with this potentiometer is contact problem. It's a contact problem resulting out of wear and tear between the moving and fixed part. So moving and fixed part. So wear and tear will happen in the contact during the contact, and as a result, after prolonged use, the contact may not be proper. That is the result. As a result, even though this potentiometric measurement, potentiometric displacement sensing is simple, the application wise they are limited. So that is potentiometers. Now inductive type of sensors. The example is LVDT, linear variable differential transformer or transducer. And this LVDT works on the principle of variation of mutual inductance. We will study in detail about the LVDT in the coming slides. So it is one of the most popular type of displacement sensor. It has good linearity. That means linearity means we already discussed input by output, the variation or relationship is linear. Can be expressed by y is equal to mx or y is equal to mx plus c. That is linearity. So that is the expected output. That should be linear. So this LVDT is a good linearity or a wide range of displacement. Moreover, the mass of the moving body is small and the moving body does not make contact with the static part. Here we can see resulting out of wear and tear between the moving and fixed part. This is static part. So there is no contact between moving and fixed part. So minimizing the frictional resistance and wear and tear. Okay. So that's about inductive type of transducer. So rotary variable differential transformer or transducer, that is RVDT. This is similar to LVDT. Similar to construction is similar to LVDT, and but the core is designed in such a way that when it rotates, the mutual inductance between the primary and each of the secondary coil changes linearly with the angular displacement. That is, when the core is rotated because we need to measure rotational motion, the angular variation. Now we have a capacitive sensor. So here the displacement measures. We have already discussed about the capacitive transducers. So in capacitive types of sensor is a versatile one. It is available in different size and shape. It can also measure very small displacement in micrometer range. The capacitive sensor can be found by either by varying the separation, the area or permittivity. That is the permittivity of the medium. You have two plates separated by a dielectric medium. This permittivity. So that is the capacitive sensor. Now we have an optical sensor. Optical displacement sensors work on the basic principle of intensity of light decreases with the distance. If the source and the detectors are fixed, so detector and source is fixed, the amount of light reflected from a moving surface will depend upon the distance from the moving surface. So we have a moving surface like this. So it is moving like this. Then we have a light source. Reflected light source is sensed by a sensor. So here these two are fixed. This is also fixed. This is the movement, and the intensity of light reflected from the moving source will depend upon the distance. This distance. So that is used for sensing the displacement in optical sensors. So that's about the optical sensors. So we have seen different sensors. We have seen different displacement sensors, that is potentiometric sensors, inductive tie sensors, example is LVDT, rotary variable differential transformer RVDT, capacitor sensors, it varies with capacitance, the capacitance varies with the distance, medium or area. Optical sensors based on the intensity variation with the distance. Now we will study in detail about one of the displacement transducer or transformer, that is LVDT, that is linear variable differential transformer. Linear variable differential transformer, it is also called as linear variable differential transducer, LVDT, differential transformer or linear variable differential transducer. So linear variable differential transformer LVDT is a primary transducer. It's a primary transducer. That is, its output is it's a primary transducer used for measurement of linear displacement with an input range of +2 to 400 mm. +2 to 400 plus or minus 400 mm. So that can sense input in a range of this input in this range. So LVDT work on the basic principle of variation of mutual inductance. Principle of variation in the mutual inductance. That's the basic principle of LVDT. Okay, it's also called linear variable differential transformer. LVDT is linear variable differential transformer. It works on the principle of variation of mutual inductance. First we will discuss about the construction of LVDT. So LVDT consists of a primary coil. We can see a primary coil. This is a primary coil. This is a primary coil. Then we have two secondaries. This is S1 and this is S2. You can see the S1. This one is S2. They are connected. The speciality of this secondary winding is they are connected in series. You can see they are connected in series, but series opposites. You can see they are in opposite direction too. Here the coil is winding like this. Here the coil is winding in the opposite direction. So series opposite. And also here you have equal number of turns, 1 2 3 4. Here also 1 2 3 4, equal number of turns. This form two secondary winding, S1 and S2. Then we have a ferromagnetic material. Here we have a ferromagnetic coil. It's a ferromagnetic coil. This is a ferromagnetic core. It's a ferromagnetic core. Is made of annealed nickel iron alloy. It's a movable core. Okay, movable core. The measurement is connected to this movable core. That is, the movable core move with respect to the measurement whose displacement is to be measured, and an external supply is given to the primary coil. That is, the primary coil is given with the external excitation. Okay, so that's the basic construction of LVDT. Basic construction. So it is one of the most popular type of displacement sensor. It has, as I said, it has a good linearity over a wide range of displacement. It works on the principle of variation of mutual inductance between two coils with the displacement. Two coil S1 and S2, mutual inductance due to S1 and S2, and this variation in the mutual inductance between coil with the displacement. It consists of a primary winding and two identical secondary winding of transformer wound over a tubular former. It's wound over a tubular former, and a ferromagnetic annealed nickel iron alloy moved to the former. So annealed nickel iron alloy which is a core. Two secondary windings are connected in series opposite, so that the net voltage is difference between these two. So that is, since they are connected in series opposite, the magnetic field induced in this coil are also opposite in direction. Therefore, the EMF generated will be opposite in nature. So the difference is the output. When we measure this output about this connection A and B, this terminal A and B, that will be difference between two EMF, that is E1 minus E2 is the measured across AB, because they are connected in series opposite. So the net voltage is difference between the two. Here the primary excitation is given to primary winding 1 to 10 volt AC with a frequency of 50 Hz to 50 kilohertz. The input is given to here. So that's about the construction. Construction consists of a primary winding where we give the excitation. Then we have two secondary. Specialty of secondary, they are series opposite in direction with the equal number of 10. And there is a field core at the center between the primary and the secondary. That is made of ferromagnetic material. That's the construction. This represents the working. So we have primary, a supply is given, two secondary. Here the normal position, this is armature or field core is placed exactly at the center. This is center. This is placed exactly at the center. So the core having equal influence with the S1 and S2. Equal influence with the S1 and S2. So when we give a supply voltage, EMF will be generated in S1 as well as S2, that is E1 and E2. So net voltage E is equal to, when we measure using a voltmeter across this terminal, E is equal to E1 minus E2. Since this core having equal influence on the two coil, E1 is equal to E2, therefore E is equal to 0. So there is at null position, the net voltage is 0 across the output terminal. Now when we give a displacement to core in this upward direction, the core will move more in the towards the S1 than S2. So the magnetic field induced EMF in the E1 is more compared to E2, that is E1 is greater than E2 because the core has moved more towards the secondary S1. As a result, the additional or extra magnetic field will be linked with the S1 and there is a reduction in the magnetic field linked with the S2. So EMF generation will be more in E1 compared to E2. So since they are connected in series opposite, the net voltage is E1 to E1 minus E2. So that will not be equal to 0. When we move the towards downward, or armature of the field core is moved downwards, this core has more influence on S2 compared to S1. So induced EMF of E2 will be more compared to E1. So E2 will be more compared to E1. So there is a net voltage in the output terminal. So that is detected as converted as displacement. So that is the working. An alternating voltage input to the primary coil, the alternating electromagnetic force EMF are generated on the secondary coil. When the core is in the center of the secondary winding, S1 and S2, the induced EMF E1 and E2 will be equal. So since the core is at the center, the E1 and E2 will be equal but opposite in polarity. Hence they cancel each other and net voltage is 0. When external application force move the core downward, the induced voltage E2 in the secondary coil S2 increases but induced voltage in S1. So S1 is an voltage induced secondary coil S2 increased but induced voltage in S1 is decreased in magnitude. So when external applied force move the core downward, the induced voltage in the E2 in the secondary coil S2 increases but induced voltage in S1 is decreased in magnitude. They are still out of phase, due to which there is some net voltage, because since E2 is greater than E1, therefore there is a net voltage in the output. When the magnetic core moved upward instead, the induced voltage in the secondary winding S1 is increased while voltage in the S2 are decreased, and then there is a net output voltage E1 minus E2. With the help of signal processing device such as very low pass filters and demodulators, the precise displacement can be measured by using LVDT sensors. So by using LVDT sensors, the precise displacement can be measured by knowing the signal out from the LVDT. So necessary condition for secondary coil. There are certain necessary conditions for secondary coil. These two secondary coils should be connected in series. They should be connected in series, not in parallel. They must have equal number of turns. They must be located equal distance from mean position. So equal number of turns, equal distance from the mean position, and they should be connected in series. That's a condition. The advantage, the next is regarding the advantages of LVDT. LVDT exhibit good repeatability and reproducibility. That's a very good advantage. They are generally used in absolute positioning sensors. Absolute positioning sensors utilized. Since there is no contact or sliding between the constituent element, it is highly reliable. Since there is no contact, this induced. So there is no contact in the sliding between constituent elements, in the sense it is highly reliable. These sensors are commonly sealed and are widely used in servo mechanism, automated measurement and machine tools. And rotary variable differential transformers RVDT can be used for measurement of rotation. That can be used for the measurement of rotation. So we discussed about LVDT is a device which senses the displacement, and then we have LVDT rotary variable transformers, etc. And we discuss about the construction. It consists of a primary coil and two secondary coil, and these two secondary coil are connected in series opposite, and voltage source is connected to S1 through core. EMF is generated on S1 and S2, and we found that the voltage in since there is a net voltage, the EMF generated in S1 is not equal to S2. Thereby we can find displacement. Necessary for as I said, this is necessary advantage of LVDT. Application LVDT: measurement of spool position in wide range of servo valve application. Provide displacement feedback for hydraulic cylinders. It is used for displacement feedback in the hydraulic cylinders. Control weight and thickness. It can be used for control the weight and thickness of medicinal products, tablets, pills, etc. For automatic inspection, final displacement of products being packed for dispatch. Automatic inspection of final product is packed for dispatch. To measure the distance between approaching metal during friction welding process. To measure distance between two approaching metals, we want to measure the distance between two approaching materials, and we can, during welding operation, we can use this LVDT. To continuously monitor fluid level as a part of leak detection. So that these are the applications of LVDT. So that's about LVDT. So we found that what is LVDT, what are the application of LVDT, social importance of LVDT, and advantages of LVDT. Advantages of LVDT. So that's about lecture number 3, and that's the end of the module number 5. Thank you.